I can fight monsters, I can't fight physics.
Hello, Year 11. So, welcome to my Physics Paper 2 Predicts for AQA GCSE Physics. Okay, so we'll start off with the required practicals that I think will be coming up. So, let's have a look at what I think. So, from the last few years, we've noticed there's a lot of questions on the required practical regarding reflection, refraction. Okay, so I'm not expecting anything on that again. Okay, the number one RP6 force and extension, nothing for the last 3 years, so therefore I think this will come up. Nice little 6 marker procedure, nice little practical to do, nice little graph to draw, and a bit of safety and accuracy to talk about. RP7, Newton's second law, force and acceleration, that came up last year, but it came up in terms of calculations and a bit about. I think there was a graph. I'm not sure. Okay, so maybe that could come up because I haven't done a 6 marker on that. Well, the 6 marker on that is a bit difficult to describe, as you'll see. And then RP8 waves, ripple tank and a string. Those are 2 separate experiments. That hasn't come up. In fact, it hasn't come up for 3 years either. So I'm expecting maybe that as a mini practical, not necessarily as a 6 marker, but we'll go through what needs to be done for those anyway. So let's start off with Hooke's law, RP6, F force and extension. So first of all, let's just go through some of the theory. Okay, so let me just sort my pen out. So what do we know? We know Hooke's law, and that simply states the extension is proportional to the force applied within elastic limit. So there's your definition. So if you look at the formula, F is equal to KE. So if you did a graph of a force against extension and you applied this equation of straight line, so a graph of force on the y-axis against extension on the x-axis, that means the gradient of this graph is equal to K, the spring constant. Or look at it the other way, K is simply F over E, and that's a rise over run or changing y over changing x. Okay, so that's the theory behind it. What could they do to catch you out? What if they gave you an extension force graph? Okay, so still obeys Hooke's law. How do you know it obeys Hooke's law? Goes through the origin and is a straight line. This time, well, what's the gradient equal to? That's equal to E over F. Well, if F over E is K, then E over F is 1 over K. So just be mindful of that. Okay, so the experiment itself, so if I show you the diagram from the textbook, okay, here you go. So you just get a spring, measure the original length using a ruler, make sure the ruler is vertical, as close to the spring as possible. How can you make sure it's vertical? Use a set square or use a protractor, either or. Okay, so place it there. Set square is perfectly 90 degrees, so you know you're measuring the correct length. Make sure you look at eye level to avoid parallax, which is a random error. So human error falls under random error. Don't say human error. And also you could put a pointer. Okay, so you could watch the extension as you keep adding the masses. So simply add more masses, measure the new length, calculate the extension, which is new length minus original length, and repeat up to, so in the case of this graph, start at 1 Newton, okay, and work your way up to 5 Newtons. Okay, it says weight, but usually they give you the mass. Okay, so if they give you the mass, don't forget the force is equal to the weight, which is equal to mg. And this normally is given in grams. So you got to convert that to kilograms first before you use weight equals mg, which is the force. Safety, usual stuff. Clamp, stand to the bench. Take care with falling weights. Eye protection. You can say you wear steel toe caps. Make sure the clamp and everything is at the middle of the table so it's not falling off the edge. You might even want to put a weight on the stand. Okay, things like that. So if I show you, if you look at this question here, describe a method student could use to obtain the results. You should include a risk assessment for one hazard. So basically, what could go wrong? What are you going to do about it? Your answer may include, so drawing that. So what's right? If you drew that, that's great. If you don't, then you're going to have to write set up a clamp with a clamp stand with a clamp, hang the spring from the clamp, use a second clamp, etc., etc. Well, the first few bullet points you could probably just put it in a diagram and you'll get the marks anyway. So risk assessment, just basic stuff. So have a read of that. Make sure you can write this out. Pause the video, write it a few times or whatever. However you learn. Okay, hazards, what could go wrong? Spring could break, come loose, fall off, things fly around. Risk, damage to your eye, wear safety goggles. And then if I just show you another one from a previous year. These are not for the last 2 years, by the way. So these are really, really old. And they're here, rather than talking about safety, they're talking about how to improve the accuracy. So we sort of talked about that. Ruler's vertical, use a set square or a protractor to make sure it's vertical. Make sure it's close to the spring as possible to avoid parallax error when you're reading off. Okay, just saying repeat is not enough. Repeat, taking measurements, ignoring anomalies or repeating anomalies is what you're expecting. Okay, so nice, easy, practical. Lots to talk about. Variables, safety, and the method itself. They can give you data, plot a graph. Just remember, is it a force extension graph or is it an extension force graph? So that is RP6, which is Hooke's law. The next one, RP7, which is Newton's second law. So Newton's second law, and I think this was chapter 11. Okay, so force extension, RP6 was chapter, I think that was chapter 11. This is chapter probably 10. Okay, so this one simply stated the acceleration is proportional to the resultant force, and therefore you have this formula, F equals ma. So if you can change the force, so this mass, from the mass you can work out the weight, which is mg, and from that you could work out the force, because the force is the weight, and that's the force in question here in the formula. Okay, so, and then for adjust the forces, work out the acceleration at the bottom, and use that to determine the mass of the system. Okay, so the key point here, this is the mass of trolley plus the weights. Okay, so it's the whole system, because the whole system is accelerating and falling. Okay, so if you drew a graph, again, if you did y equals mx plus c, let's draw that again. So if you did a force against acceleration, because that's y equals mx plus c, so the gradient here would be equal to the mass. But if you did the other one, if you did an acceleration force graph, because force is the dependent variable, acceleration is the independent variable. Again, you're going to get a straight line, but this time, this is now equal to a over f, which is the same as 1 over m, okay? Whereas this m is equal to f over a, just rearranging the formula for m. Okay, so things to do, things to work out. So if you remember from the previous 2024 paper, you're trying to work out the acceleration. Okay, so a number of ways you could do that. You could just simply do v minus u over t, where u equals 0 and v is equal to the distance over the time. Okay, and then once you've got that, how do you work out the speed accurately? Well, don't use a human being, just use a light gate or a data logger or some sort of motion sensor. Or the other way you could do it, from that, maybe you could use v squared equals u squared plus 2as. Again, rearrange that for a. Okay, s is the distance, u squared is 0, obviously, so that becomes v squared equals 2as. So you could do that way, and then plot a graph of the force and the corresponding acceleration. So again, haven't seen that as a required a method. Very difficult to sort of write as a method because there's so many quantities to put in order, but they could possibly do that. But at least you should be able to write out the formulas and what you're measuring. Basically, increase the mass on the mass holder and measure the speed of the trolley at the end. Why do we have it on a slope? The slope is to negate the effects of friction. Okay, so some things you just have to think about. And if you look at the past paper questions when I made these exam packs per required practical, you'll see the sort of things they're asking. So those are the two main ones, two big ones that I haven't asked in terms of methods. Okay, so let's move on to required practical 8. So this is the ripple tank. So there's two types. There's the ripple tank, and then there's the standing wave. So this one, what do we know? These things are called wave fronts. So if I was to draw them from the bird's eye view, what do you know? The distance between the wave fronts is lambda. Okay. This ripple tank, usually the way they're set up, they look like they're stationary. So you could work out lambda using a ruler. Or more importantly, you wouldn't measure across one because there's a huge reading error. You'd measure across so many. Let's call that x. Okay, so that's 1, 2, 3, 4. So here, lambda would be equal to, in fact, let's call it average lambda is equal to x over 4. Okay, so that will be good practice. So that's like an averaging technique. All right, so you can work out lambda if you know the frequency of the vibrating bar. Okay, then from these two, you can use V equals F lambda. And all you do, just vary lambda, vary the frequency, measure the corresponding lambda, and work at the wave speed. The way they've done it here, so teacher measures the time taken for 10 waves to fronts to pass the mark. So let's call that time t. If you know the time taken for 10 wave fronts, you can then work out the time period. The time period is the time for one. So you simply just do t over 10. Now, once you've done that, well, what you're going to do with this t, you can then work out frequency, which is 1 over t. And then you can put it into V equals F lambda. Pen's playing up there. Let me just rewrite that. So from that, you could do V equals F lambda. Okay, there's not much you can say really in terms of procedure-wise. Your teacher probably set this up. I know I think I ended up doing it as a demo for myself or showing it as a video. I can't remember. The other version of the wave speed is this one. So what do we know? This one whole loop, two loops is equal to one wavelength. Okay, so you can measure that using a ruler. Okay, this here is your frequency. So when you got those two, what can you work out? You can work out the wave speed. Okay, and all they did, I think there was a procedure with this one, only like 4 marks. Change the masses, you'll lose the loops, and then alter the frequency until you get this double loop back. This double loop is your wavelength. Okay, so if you look here, so it's only a 4 marker, it wasn't a full 6 marker. Add or take away masses, so you're changing the tension in the string. Adjust the frequency or move the bridge, one or the other, or do both, until you get this double loop again. And then if you get this double loop, then you know you've got one wavelength. And then note down the frequency, note down the wavelength. Don't forget, this has got to be in meters. All right, if you want wave speed in meters per second. So just be careful because there'll be a lot of looking at the units or just checking your units because they've given you the formulas now. So again, just have a read of it, really straightforward. So those are the 4 I'm expecting. Out of the 4, I'm expecting the first 2 to be heavily done. These probably has a little mini question. Okay, maybe they'll link it with a waves question from chapter 12 or something. Okay, so let's move on to the chapters themselves then. So let's move on to chapter 8. What am I expecting from chapter 8? Okay, so chapter 8 is just forces, Newton's first law, Newton's second law, Newton's third law. Newton's first law just simply states if the resultant force is 0 or the forces are balanced, it doesn't move or it's moving at constant speed depending on what it's doing in the first place. If the forces are unbalanced, there's Newton's second law, i.e. one force is bigger than the other. That means there's a resultant force. If the resultant force has an acceleration. Okay, that's Newton's second law. All right. Newton's third law is separate to those. So basically, if I exert a force on something, that something exerts an equal and opposite force back on me. Okay, if that causes me to change direction or speed up or slow down, then that then becomes Newton's second law. But if, let's say I'm just leaning against the wall and I'm not moving, then that suddenly becomes Newton's first law, doesn't it? Okay, because we're stationary, right? Or the forces are balanced. But the higher part of this chapter was all about vectors, not scalars and vectors, but drawing vector diagrams, parallelogram of forces, resultant vectors, resolving vectors. Okay, so let's do the first one where you work out the resultant. So look at this question here on the left. Resultant force of the tow bar on the trailer has a horizontal component and a vertical component. Okay, horizontal force is 200, vertical force 75. Now, it doesn't tell me whether it's left or right or up or down. I'll sort of cut the rest of the question out. But you'll be able to work it out from the picture, as we're going to see in the next question. Determine the magnitude, direction of the resultant force. So what you got to do first, you get your first mark. These would be like 4 markers or something. You're going to have to do a scale. So if I said 1 centimeter is, let's say in this case, 10 newtons. Okay, that means that becomes 20 centimeters and that becomes 7.5 centimeters. Okay, choose your own scale. Look at the page you've got. Look how much space they give you. What can you fit in there? And obviously, the bigger the picture, the better, the easier it is to read off anything. So the question is, what do you do? You draw what you could possibly draw what we call a triangle of forces. Okay, so you draw one of them first. Now I'm going to draw the horizontal because that'll be the easiest, and probably the easiest for you if you've got a ruler. So it'll be there, and that will have to be 20 centimeters long. And then at the end of it, I'm going to draw the vertical one, and that is your 7.5 centimeters. And then, well, how do you work out the resultant? You just simply join them up. Okay, now which way is it going to go? Is it going to go this way? Well, if you push to the right and you push up, you're not going to the left and going down. Okay, so use your common sense here. Where you're going to end up, you're going to end up that way. Okay, so if I was to work that out with my, you've drawn a scale diagram, by the way. So let's say I've measured that and I've worked that out to be 23 centimeters. Well, then I know it's times that by 10, so that's 230 newtons. So there's the magnitude. And how do you work out direction? You get a protractor and you work out either this angle to the horizontal or you work out this angle to the vertical. Choose one, but make sure you state which one you've chosen, like 230 newtons at 24 degrees to the horizontal. Okay. Any pitfalls here? Yeah, now you could actually do this by Pythagoras, okay, but they're not going to ask you. If you look, it says determine by drawing a vector diagram, and that's what they're expecting for 4 marks. If you do calculation only, you probably won't get anything. Okay. If they're generous, they might give you 1 mark, but the time it takes to do the calculation is the time it took me to draw this. Now, what's the opposite of this is when they give you the resultant and they ask you to work out the horizontal and vertical vectors. Okay, so every vector can be resolved into a horizontal and a vertical component. So tension force in the cable can be resolved horizontally and vertically. Tension in the cable is 2000. Cable makes an angle of 20 degrees to the horizontal. Draw a vector diagram. So basically, they're giving you the hypotenuse, which you have to draw to scale accurately. And then from that, you've got to work out the horizontal and the vertical components. There's going to be a bit of leeway. Okay, it's not going to be perfect because they normally don't give you lined paper. They just give you this sort of plain paper. Okay, so what you do, well, straight away, I'll probably say 1 centimeter is, I'll just say 1,000 newtons this time. Okay, so it's not going to be very big. So if I draw a line, find a horizontal benchmark. Okay, maybe a line parallel to the edge of the bottom of the paper. Put your ruler on there. Work out 20 degrees. I've just exaggerated this, by the way. Okay, and then draw your line. So there's my 2 centimeters. And this is obviously downwards. Now that's important. And then to the dotted line, draw your vertical line downwards. Okay, so I'll call this vertical. And then this will be your horizontal. Is that going to straighten up? No. So let's try that again. This will be your horizontal. Make sure they all join up. Okay. So that's the horizontal. And then work out what they are in centimeters and use your scale to work out what they are in newtons. Okay. So let's have a look at how can they make it harder. Is not when there's an angle of 90 degrees between the 2 vectors, or there's an angle other than that. All right. So in this case, we've got this picture here. This is not drawn to scale, so I've got to sort of work out a scale. So I'm going to do it on the picture. Okay. So now you could do it on the picture, or you could find some vertical line as a reference point, because you want to. If you get the vertical line wrong, you're going to get the other one wrong as well, because it's all going to be relative. So here, I would probably choose 1 centimeter is 1,000 newtons. Okay, so straight away, I know if you push in the direction of A and you push in the direction of B, you're going to go somewhere in between. Now, if all you did was draw that line, I'll obviously use a ruler, you'd get 2 out of 4 marks because A, you determine the direction of the resultant force, and B, you realise the resultant force here is bigger than any of the 2 because they're working together. Okay, they're not going in opposite directions, but there's no reason why you can't just work it out properly anyway. So what do you do? So this is where you draw your parallelogram of forces, okay? Now, this is specific on the spec, and it's, the whole textbook pages or double pages on this. So doing triangles like we did before, don't worry about that. Just stick to parallelograms. So now they've drawn two lines for you, but they're not to scale. And let me just check with the protractor. So according to the protractor, I've just got this protractor, I'm placing it on my computer screen. This angle is perfectly 45 degrees. Okay, so if it's not, you're gonna have to draw it. So let me draw a line. So if B is 2000, so I've got to draw a line of 2 centimeters. So let me just draw that first. And I'm going to use theirs as a benchmark. So there is the first one. So there is my 2000 newtons. And then I'm going to draw the other one on it. Okay, it's 4 centimeters. So that is here. Okay, so let's put 4000 newtons. Now, what do we now do? We've got to draw, we've got to finish off the parallelogram. So along this line, at this point, I've got to work out here another 45 degrees. So I'm just going to put my protractor on that dot. Okay, and work out 45 degrees. So 10, 20, 30, 40, 10, 20, 30, 45. So it's there. So then I'm just going to draw parallel rays, make sure the lengths are exact. So I'll draw the diagonal first. So that's 4 centimeters. So it's going to be there. Okay, and then I'm going to join it up. So you should get something that resembles a really decent parallelogram. Okay, so draw the arrows showing direction if you want. And then where's the resultant? As we said, where's from the beginning to the end where the lines meet. So again, get your ruler, draw it. So that is 55.7 centimeters. So don't forget to draw the arrow. So 5.7 centimeters, which is 5,700 newtons. And then, because it's a vector, you've got to give an angle. So give an angle to the vertical in this case. Okay, if one of them was horizontal, give it to the horizontal. Give it to something that's easy to do. And if I just get the protractor on that, just give me a second. So the protractor on that is 30 degrees. So 30 degrees to the vertical. Okay, so that's what they're expecting. Okay, so I've sort of helped myself by using their diagram as a template. Okay, obviously their lines weren't to scale, so I've had to adjust it to my own. If you want to draw yours over here, you're more than welcome to on the space. But then straight away I can tell my first line is not vertical, so I know I'm going to be out by a little bit. But they give you a tolerance anyway. Okay, so moving on, here's an AQA one. The one I just did with you was actually from Cambridge International. So this is drawn to scale, so I don't need to do anything here, but I do need to work out, well, if that's 300 newtons, well, how long is that? So that's 300 newtons is equal to 3.5 centimeters. Okay, I'll need that in a minute. So first of all, I've just got to draw my parallelogram. So in order to draw a parallelogram, I'm going to work out the angle between them first. So that is 40, so that's 40 degrees. Okay, so if I was to extend this line, okay, and then I've got to work out 40 degrees at the tip of that arrow. So it's there. So you'd have done a lot of this geometry style stuff at GCSE, I'm hoping. And then I've got to now draw a line of 3.5 centimeters. So from the tip of the arrow to that there. So 1, 2, 3.5. Going to be a full line. Okay, and then I can join it up here. This one is going to be 3.5. Okay, trying to put a ruler on a screen is not very easy. Okay, and then, well, we know where the resultant is, again, from the beginning to where they join up, and that is exactly 6.5 centimeters. So I've got to work out my scale first. So this is 6.5 centimeters. So what I'll do, I'll work out what 1 centimeter is. So to do that, you just do 300 divided by 3.5. Okay, so that gives me 80, I'll say 86 newtons, and it's times that by 6.5. Okay, you might have your own maths method, but that's up to you to do. Okay, so that gives me 557 newtons. And then I've got to work out an angle. I'll probably give it, this case, here, theta, to the horizontal. No, it actually says they just want the resultant force, but let's just do it anyway, just for good practice. So I've got 10, 22. So at 22 degrees to the horizontal. Okay, so these are the toughest bits of chapter 8. Okay, other things on chapter 8 that come up. Make sure you know moments. Okay, they're not going to be a straightforward example. So just be mindful of that. This one, well, what you got? You got a pivot here, haven't you? This one is a clockwise moment. And this pulling force, the tension in the wire, that's an anti-clockwise moment. If it's horizontal and if it's in equilibrium, 2 facts you need to know. Okay, in equilibrium, so the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So I can work out, because I've got the force and the distance for the clockwise, I can work out the force for the anti-clockwise. So the clockwise moments is 600 newtons times 6.4. Just check all your units. These are fine. Okay, is equal to force, the pulling force, times 2.4. Okay, so you can work out F there. Okay, now in equilibrium, this is the first thing that happens. Also, the second thing is that the net force is 0. And you've probably seen this before because it's essentially Newton's first law, isn't it? Now, when you look at your answer, also, look at the answer. Does it make sense? If you're closer to the pivot to produce the same moment, your force must be bigger. Okay, so the force is going to be bigger than 6,000. Okay, so just to prove it to you, 6,000 times by 6.4 equals divided by 2.4. So that gives me 16,000. All right, so look at your answer. Does it make sense? Yeah, if you're closer to the pivot, you need a larger force. All right, so that's a nice one. So let's look at some nasty ones. Okay, so we got this question here. So it shows the ramp partway down in a balanced horizontal position. So if it's balanced, okay, what do we know? We know the sum of the clockwise moments is equal to the sum of the anti-clockwise moments, and the resultant force is 0. Well, clearly this looks like, as soon as I mentioned pivot, I know it's not a resultant force question. It's clearly a moments question. Now, they told me the moment caused by the weight of the ramp. So that there is your anti-clockwise moments, and that's equal to this. They told me the spring is stretched, so they give me the extension and calculate elastic potential energy. So elastic potential energy, go straight to your formula sheet. E P is equal to half K E squared. So we've got the E, but we haven't got K. So can we work out K? Yeah, because as soon as you see springs, you should be thinking F equals KE. Okay, so therefore, can we work out F? Well, yeah, because you just got your standard seesaw, haven't you? So there's your seesaw. Here's a force that we're trying to work out. They've got that distance, 0.15. Okay, well, they've actually just told us this moment. Okay, so 924 Newton meters. So that is your anti-clockwise. So if you just follow down from the formula, 924, and the clockwise is equal to F times 0.15. Okay, and as we said, because F is so close to the pivot, it's going to be a large force. So if you did 924 divided by 0.15, so that gives you a force of 6,160 newtons. Now, what can I do with that? I can then put that into F is equal to KE, or K is equal to F over E. So in this case, just put your numbers in. So F is 6160 over the extension they've told us is 0.250. So answer divided by 0.250 equals, so that gives you a spring constant of 24640 newtons per meter. It doesn't mean anything to you, but at least we can now put that into here. Okay, and this was a 6 marker, I think. Okay, so it's a half times 24,640 times 0.250 squared. Okay, so put that times 0.5 times 0.250 squared equals, gives you an answer of 770 joules. Okay, so expect some paper one calculations in the mix now. Okay, because the assumption is you've done a paper one. Okay, let's have a look at an even nastier question. All right, so again, moments. Figure 2 shows a small weight placed on the insulating bar makes the wire X go back and balance. So if it's balanced, what do you know? Sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Okay, so they give lots of information. So the small weight causes a clockwise moment of. So we got your clockwise. Okay, that's your clockwise moment. So that's 4.8 times 10 to the minus 4. So if you think, well, there's your pivot. Okay, there's the clockwise moments. So there must be a force here causing a anti-clockwise moment. Okay, so from that, let's calculate magnetic flux density. Now, what's the only formula you see with that? F is equal to B-I-L. Okay, so again, you've got all the formulas. So to work out B, I need I. Well, here's I. And have I got L? Yes, L is here, but it's not in the right unit, so 0.05 meters. Okay, so then I could rearrange and work out B if I know F. So I can work out F here, because this F times this distance, which is 0.08 meters, 0.08, will give you a moment of 4.8 times 10 to the minus 4. So you can work out F. So let's put it all in really quickly. So 4.8 to the xp minus 4 divided by 0.08. So that gives you a really small answer. So I was expecting that. So let me just check I've done it all right. So 4.8 to the xp minus 4 divided by 0.08. Yeah, so I've got 0.006 newtons. Okay, so what can I do? I can now put that into here. So 0.006 is equal to B times 1.5 times 0.05. So I can work out B is simply 0.006 over 1.5 times 0.05. So put it all in, so answer divided by open brackets 1.5 times 0.05 close brackets, that gives me 0.08, and the units of magnetic flux density is T or Tesla, either or. Okay, so that's sort of question you could expect. Other things I can ask you about is stability. How do you make things more stable? So first one, lower center of mass, and the second one, wider base. So they'll give you a bizarre example. It doesn't matter, just churn these out anyway. Okay, and then maybe you have to apply it. Maybe some brain cells will start firing. But if it doesn't, just get these down in the least. Okay, so that is your chapter 8. Okay, moving on to now. I've put chapters 9 and 10 together. Chapter 9 was all motion graphs. And this was about the forces that cause the motion. So we're going to try and link it together, and then we'll look at sort of things they're going to ask you about. So first of all, let's look at DT graphs. Okay, now DT graphs, one thing you need to know, the gradient is equal to the speed. Okay, so if I show you the 4 variations you can get, so 2 are easy, 2 are very difficult. So expect the difficult ones. So you can get something like that, nice straight line, nice straight horizontal line. Then you get what's called an increasing gradient, and then you get a gradient that's decreasing. So here, what do we know? The gradient is the speed, y, because it's equal to distance over time, isn't it? Changing y over changing x. Okay, so constant gradients. So I'll go through all the words. Constant gradient. So always start off by describing the gradient and then replace the word gradient with what the gradient represents. So here is constant speed. Okay, here, 0 gradient, so 0 speed. Okay, that must mean it's stationary. Okay, here, what do you know about the gradient? The gradient is increasing. So therefore, the speed is increasing. Therefore, it's an acceleration. Okay, so see how I worded that? I started off with what does the gradient represent? There's only one fact here that you need to know. And then what have you got here? The gradient is decreasing. So if the gradient is decreasing, the speed is decreasing. Pen's playing up again. And therefore, what's another word for speed decreasing? A deceleration. Right. Now, how do these look like if I drew these same shapes on a speed time graph? So let me just redraw them. Okay, so let's just draw them again. So just be careful with these. So first of all, on a speed time graph, what do we know? We know the gradient in this time, it's equal to the change in velocity over the change in time. Change in velocity over time gives you the acceleration, and the area is speed, velocity times time, or speed times time. Speed times time is equal to the distance. Okay, so they'll expect you to use those. So what do we got here? We got constant gradient, constant acceleration. Here, zero gradient, zero acceleration. So it's not accelerating, but it's not stationary because it's got a certain speed. So here it's a constant speed. It might have a constant speed of zero if the horizontal line was right at the bottom. Here, what do we know? The gradient's increasing, so the acceleration is increasing. And here, gradient decreasing, so therefore the the acceleration is decreasing. It's still speeding up, okay, because the line's still going upwards, but it's not at the same rate as before. So it's like if you think of the last one, slam your foot on the accelerator, your acceleration, you get a huge boost, and then you just slightly take your foot off the accelerator pedal. You still got your foot on the pedal though, because your speed's still increasing, but you just haven't got that boost or that kick anymore. Okay, so that is all the motion graphs, essentially, really, for chapter 9. It's a really short chapter. Then how do we link it to forces? Okay, so let's go through what we remember. So if we go on to the next one, so this is now chapter 10. So Newton's first law stated when the resultant force is zero or its balanced forces, then what you get is constant speed or you're stationary. Okay, and we'll link all this in a minute. And then Newton's second law stated when there's a resultant force, that will give you an acceleration, or F equals ma. So that means one force is bigger than the other. So therefore, that will create an acceleration. So let me just show you a classic graph. So if I said to you a VT graph this time, so we're going to try and, let's say this was a car. Okay, so what do we know? First bit, constant gradient, let's say this was a car, sorry, yeah. So this was your car trying to go this way, all right? So here, what do you know? Well, you're accelerating, so there must be a resultant force. So that must mean there's a force this way, and there might be a small force this way. Okay, didn't come out right. Okay, so therefore there's a resultant force. Now, what do you know here? Constant speed, Newton's first law, so that must mean the forces are the same. Here, what do we know? If you look at this one, you've got an acceleration, and the acceleration is greater. That means the resultant force is greater. So maybe you put your foot on the accelerator, and therefore the resultant of these two forces is much bigger. Here, what do you know? Well, it's constant speed, so Newton's first law, so the resultant force is zero, so the forces are balanced. Okay, so for whatever reason. And then here, we're still moving this way, by the way. Now you're decelerating. That means the force backwards is bigger than the force forwards. In fact, there might not be a force forwards because you put your foot on the brakes. Okay, so can you see how you can visualize that in terms of forces, hence forces and motion? All right, so let's look at a classic question. Okay, I say classic question. They've given a not so classic graph. Okay, so an aeroplane is 4,000 meters above the Earth's surface. A skydiver jumps from the airplane and falls vertically. Figure 1 shows the distance a skydiver falls during the first 12 seconds. So if you look here, you got this bit increasing. So this is a DT graph. So the gradient, so here, the gradient is the speed. So you've got a gradient increasing, therefore the speed is increasing, so therefore you've got an acceleration. Then look at this bit, you've got a constant gradient, so therefore you've got a constant speed. Okay, so this one must have been Newton's second law. This one was Newton's first law. So it's skydiver falling. So what do we know? Initially, as you're falling, the force downwards was bigger than the force upwards. And when you get to this point, obviously, I don't know why you've got heavier, but you have. But let's draw it again. So what do you know this time? The force downwards and the force upwards are equal. Okay, so let's look at the classic graph they would have given you, and let's just give an explanation that you could use in the exam. So this hasn't come up for a while, that's why I'm going over it. So this is your classic VT graph, and it levels off. Okay, so VT, and then we'll look at the what ifs, what they could ask you. So can you see here? What do we know? The gradient is the acceleration. Okay, so initially, if you was the parachutist here, you've just got one force and a resultant force downwards, so you accelerate downwards. Here, what's happening to the gradient? The gradient is getting smaller, so the acceleration is getting smaller. That must mean the resultant force is smaller. So that means your force downwards has stayed the same, but the force upwards is increasing. So your resultant force is smaller. And when you get to here, force downwards and the force upwards is equal, or the drag is equal to the weight. Okay, so now let's put this into 3 or 4 sentences that you could use. So you could say initially, resultant force is equal to the weight. So the acceleration is maximum, which is equal to g. Okay, so you're still accelerating. So then as speed goes up, drag increases. So if drag increases, the resultant force goes down. The resultant force goes down, the acceleration decreases. Now you can actually write like this. You don't have to put words, or these symbols are right, everyone understands them. And then what happens next? If you look up here to the last bit, eventually the drag equals the weight. So the resultant force is 0. So the acceleration is equal to 0. Okay, so therefore that's the constant speed, or your terminal velocity. Okay, then what do? We could draw the next bit. So then you open your parachute. So what happens here when you open the parachute? Okay, your legs and arms are still there. So your weight is there. What your drag is now, sorry, your drag is now much bigger. So the resultant force is upwards, even though you're moving downwards. That's like you trying to run forwards and someone drags you back. So you decelerate. Okay, and then eventually the last bit, what happens in the last bit? So as you're decelerating, as your speed decreases, drag decreases. So you get to the point here, even with the parachute open, the drag is equal to the weight again. Okay, they've never usually asked about these last 2 bits, but they could do. And then let's look at what are the what ifs they can ask. Okay. So classic what ifs with these sort of questions. So if you got a VT graph and this was the parachutist, let's say, what would happen if it was a, let's say, for example, it was a car. So at this point here, the drag equals the weight, doesn't it? So if you're a car, your weight is greater. If your weight is greater, then the drag required, it needs to be bigger, okay? Because it needs to be a bigger number, because the weight is a bigger number. Therefore, how do you build up drag? You need to build up speed. So ironically, to get a bigger drag, you need a larger speed. To get to that larger speed, it takes longer. Okay, so if I was to draw, oops, sorry, keeps doing that for some reason. So look at the point where terminal velocity is reached. I'll just put TV. TV. Okay, so let's call that a person, and let's call that a car. So greater weight needs greater drag, needs so needs more time to build drag and greater speed. Okay, and then if you used to do, let's say, a piece of paper, less weight, so therefore needs less drag, so will reach its terminal velocity earlier because the drag will equal the weight earlier. So it'll be something like this. So there's your TV for a piece of paper. In fact, it's probably less. So just remember, the heavier you are, the higher your terminal velocity and the longer it takes to reach it. Piece of paper, very light, reaches terminal velocity earlier and a lower terminal velocity. Okay. Other things that affect the drag could be air resistance. There used to be questions like, well, what if you dropped the parachutist was on Mars, which has a more dense atmosphere? Well, clearly more dense atmosphere builds up the drag earlier. So we'll reach its terminal velocity earlier and therefore we'll have a lower terminal velocity. So can you see just what ifs? Like, but the most important thing at TV, at the terminal velocity, drag equals weight. Okay, so that's what you just write that down first up. Okay, and that should help. Now, the word drag, they might be a bit funny with that. Use the word air resistance if you have to, if you're not sure. Okay, so let's have a look at a question about it. So you've got this one here. So a racing driver is driving his car along a straight level road as shown in the diagram. The driver pushes the accelerator pedal as far down as possible. And then, so you've got an engine force, let's say, and clearly we've got some frictional force. Okay, whether it's the air resistance or the friction from the ground, that could be the total or the result of all that. Explain the reasons for this in terms of forces acting on the car. So when you're accelerating, let's put this down. So when you're accelerating, the force forwards is greater than the force backwards. Therefore, there's a resultant force this way. Therefore, there's an acceleration this way. Okay. Then, as speed increases, because you're accelerating, do that again. As speed increases, drag increases. So therefore, the resultant force decreases, therefore acceleration decreases. But you still got an acceleration, but it's not as big. And then eventually, now we don't say drag equals weight because those forces are 90 degrees to the motion. You only do that for falling objects. Well, so we look at the two forces. Eventually, Fr is equal to Fe. So therefore, we've got a resultant force of 0. So therefore, you've got an acceleration of 0. So therefore, you've got a constant velocity, or you've got what we call a terminal velocity. Okay, so that's sort of forces of motion questions they haven't asked yet. So have a look out for those. Okay, moving on to chapter 11. So chapter 11, we already talked about a bit because that was the Hooke's law experiment. Okay, so let's think about what else they could do. Now, chapter 11, they've actually gone through quite a lot, actually, because they've done a lot of sort of things you got to look out for. Pressure equals force over area. And also pressure is equal to rho GH in fluids. Or liquids in most of the questions seem to be about liquids, and there's quite a few questions, quite a few nasty questions actually. Let's do a question where we can put it all together. So let's say, for example, you've got this this is a seabed, and at the bottom of the seabed you've got this treasure chest. Okay, and there's the lid. All right, so let's say this is 80 cents. What's going on here? 80 centimeters by, let's say, 40 centimeters. So straight away, when you see some sort of dimensions, is it length, is it volume? Is it area or so on? So that's what you got to think of. And let's say this is at a height of 30 meters below sea level, and the density of water is about 1,000 kilograms per meters cube. Okay, so meters cube, centimeters, meters. Look carefully, look for unit conversions. So the question is, calculate how much force is needed to lift the lid. Okay, so this is the reason why they probably don't lift the lid underwater. Okay, they wait till they bring it to the surface. So let's have a think. So, right, okay. So what we got to work out force. So you can see we've got some force here. So we've got pressure equals force over area. But the force we can work out, oh sorry, we're going to calculate the area we can work out. So we can say the area is 80 by 40, but it's not 80 by 40, it's 0.8 by 0.4. Okay, so that's your area. So if you put that in, well, it's just 8 times 4, then just do your scaling. So that should be 0.32 meters squared. So I've got my conversions already. All right, so there's the first mark, isn't it? Now we want to work out the force. We've got the area, but we need the pressure. So what pressure exerted on that lid is liquid water pressure, isn't it? So the force over the area must be equal to the rho GH. And G is always 9.8 newtons per kilogram. Okay, and they'll give you that, and they tell you that in the question. Clearly, you're going to use it. So look for your formula sheets. Where am I going to use G? W equals mg. I don't need to use it here because I haven't been given the mass. Where's the other time I see G? Rho GH. Okay, MGH. MGH is not a question about GPU. Okay, so it's going to be rho GH. So what do we know? So force over 0.32 is equal to the density times 9.81, and the height is actually the depth times by 30. So we put it all in. So that's 9,000. Actually, I've used 9.81 there, which is actually A level. There's no harm in using it, but I guess stick to 9.8. So 9,800 times 30. Okay, so and then F is simply that number, 294,000 times by 0.32, because we're going to take the 0.32 over 0.32. So that gives you an F of 94,080 newtons. So that's how much force is exerted on the lid. That's how much force you're going to need to lift up with, and you're not going to be lifting that up. Okay, that's like 9,000 kilograms. So the force on that lid is immense. It's like 6, 7, 8 cars. Okay, and you're certainly going to lift it. So you may as well take it out of the water. So raise it out of the water using the crane or whatever they use, and then lifting the lid there, because then it'll just be the weight of the lid, which will probably be about 3 or 4 kilograms at most if it's wood. Okay, so that's sort of classic questions. The other thing they haven't tested yet, really. So this is all the formulas for that. So just be mindful. That's like quite a challenging question because a lot of things in there. Is they haven't talked about upthrust very much. Okay, so what is upthrust? So anything that is in water experiences upthrust. So if you think of, let's say you've got something in the water, you've got the weight downwards. Why does it float? Because there's an upthrust upwards, and the weight equals the upthrust when you float. If you sink, okay, if you go to the bottom, let's say you're there, clearly you got a weight. You've still got an upthrust because the upthrust is due to the pressure difference on the top and the bottom. So the pressure on the bottom of the box is greater than the pressure on the top of the box. So there's a pressure difference. Here, the weight is greater than the upthrust, so you sink. There is upthrust, you just sink. All right. That's why when you're in water, you don't feel as heavy as you would normally because the upthrust is helping you. Right. So make sure you can explain that. Then the other thing they could ask you, well, what is upthrust? So upthrust is equal. Well, we know what it is. It's a force acting upwards in fluids or liquids in this case. Its upthrust is equal to the weight of the water displaced. So I'll give you a classic example. Let's say you've got a bath sponge, and the bath sponge, in fact, let's just draw it. As you know, they're really light. So the bath sponge barely, so this is your sponge, barely, it just sits on the, it looks like it's sitting on the water up until the point it starts soaking water in and then it sinks to the bottom. But if you had a block of wood, which will float in water because it's less dense than water, then it'll float, but most of it will be under the water. So let's say they both had the same dimensions. So let's see if I can draw that a bit more. So let's say they had the same dimensions, all right? So why is it the wood sinks further? Can you see? The wood is sinking further, yet the sponge isn't. Well, it comes down to this thing called, well, they're both floating, so weight equals upthrust. But the wood has larger weight, so it needs more upthrust. Now, look at the definition. Upthrust is equal to the weight of the water displaced. So if you want more upthrust, you've got to displace more water. The best way to displace more water is for you to sink further in. So it needs more upthrust. So it sinks further to displace more water to create more upthrust. So keep that in mind. Okay, that's the principle behind it. All right. Now, for some of you thinking, well, how do you work out the upthrust? You could just use, I mean, there is a formula for it, but it's not on the spec. Well, I'll give you a classic example. Let's say, for example, you've got a force meter. At the end of the force meter, you've got a block of, let's say, steel. So we know it's going to sink in water. And let's say the reading on here is 30 newtons. And then you're going to place this in water. Okay, and as you know, it's going to sink, isn't it? Okay, but what you'll notice, it's not going to read 30 newtons anymore. It's going to read, let's say it reads 22 newtons. Why? Because now there's an upthrust. Okay, so how do you work out the upthrust? Well, it's the real weight minus the apparent weight, so it must have been 8 newtons. Okay, so that's the sort of, if you can get that calculation in your head, you'll sort of get the idea of what upthrust is. So let's move on to, I mean, like, what other things can they ask you about? If we just go back here, what do we know? Pressure increases with depth because the weight of the water above you. Okay, that means larger force on top, pressure is force over area. And as you go further up into the sky, pressure decreases with altitude because there's less particles, less collisions, so less pressure exerted on you from above. Okay, so therefore, pressure decreases. So here's a question that came up a while ago. So when flying, the pressure inside the cabin of an aircraft is kept at 70 kilopascals. The aircraft window has an area of, so aircraft windows, here's my aircraft window. And here's the cabin, the inside of the cabin this is. So, and obviously there's your chair. You're sitting there. Now I'm going to move you out the way. Okay, so there's your chair where you normally sit. So there's your window cabin. Now it says the pressure inside the cabin of an aircraft is 70 kilopascals. So that's 70 kilopascals, so 70,000. So just be mindful of that. This has an area of 810 centimeters squared. So we've got an issue. Why is it 5 marks? We've got an issue here. All right, so again, how do you go from centimeter squared to meter squared? So we'll come to that in a minute. So use data from figure 1 to calculate the resultant force acting on an aircraft window when the aircraft is flying at an altitude of 12 kilometers. So from the question itself, 12 kilometers, it was about 30 kilopascals. Okay, so I've just made this number up. It doesn't really matter. And then obviously an answer, a mark for 2 significant figures. So you've got a choice of 2 things to do. So we've got 30 kilopascals this way, pressure, and 70 kilopascals the other way. Now, clearly, 70 kilopascals is bigger than 30, so it's going to pop out. isn't it? All right. So we've got to work out, if you can work out the resultant pressure, you can work out the resultant force. Okay. Well, the resultant pressure is 40 kilopascals, isn't it? Okay. So if we did that, so resultant pressure is equal to 40 kilopascals, which is 40,000 pascals. Okay. So conversions. Now to work out the force, well, what formula do you know with pressure and force? Pressure is force over area. So a pressure of 40,000 is equal to F over A. Now, what is the area? Well, centimeters is the equivalent of, so if I was to write centimeters, that's a centimeter. Now, we've done millimeters. Centimeter is actually times 10 to the minus 2. So what you've got here is 810 times 10 to the minus 2 squared. So that now becomes 810 times 10 to the minus 4. Okay, so that's how you would do that. All right, so just remember that. And then, so that goes at the bottom. So 810 times 10 to the minus 4. Now, I know that's not the correct way of doing standard form, because you're supposed to have one number in front of the decimal place, but we can neaten that up later. So we've got to work out the force. So that's 40,000 times 810 times 10 to the minus 4. Okay, so if you put it all in, so 40, 1, 2, 3, times 810 to the exp minus 4. So that gives you a force of 3,240 newtons, which is a lot. Okay, so I've sort of exaggerated, made these numbers up. It's not that much, otherwise it'd have probably popped out. But then the shape of it sort of keeps it in anyway. Now, that's one way of doing it. The other way you could have done it is if you've got the pressures and you've got the area, you can work out the forces. So you'll have the corresponding forces. Obviously, the force on the inside is greater. Just work out the resultant force. Okay, so those are your sort of classic questions, all right? So that's chapter 11. Right, moving on to chapter 12. So chapter 12 is the start of all the wave stuff. Okay, so it starts off with longitudinal waves, transverse waves. Waves carry energy, they transfer energy, transfer data, but they don't transfer matter. And then it went into the higher stuff, which was reflection, refraction, which were the required practicals which they've done for 3 years in a row. So I'm not expecting that. Maybe questions on wavefronts. And again, that came up on last year's paper. So have a look at last year's paper, have a look at the walkthrough, I explained it. And then there was, so that seemed like the majority of it. Then there was this thing about sound. Obviously, we got ultrasound. And then the uses. Okay, so most obvious uses, fetal scanning. Well, not obvious to you, but fetal scanning. Another one was depth testing. Okay, so key thing to remember, yes, we've got a formula for waves, because waves we use V equals F lambda. Well, you could also use V speed equals distance over time. Okay, so when we say depth testing, it's like echo location, which is what bats do. Okay, so what that does, it sends out a beep or a sound, I guess. It travels, hits the surface, comes back. So you measure the time taken to get there and back. Divide the time by 2, okay, because you only want the time to go there. And then using speed is distance over time, or distance is speed times time, you can work out the distance or the depth. Okay, and that's essentially how these things work. They work on basically echoes. And there's usually an echo. It echoes because there's a change in density. Okay, so think of a bat sending out ultrasounds, hits a solid surface like a tree, okay, compared to the change in density, bounces back, okay. Same with fetal scanning, hits the bone of the fetus or the organs, because there's a change in density from the fluid, the amniotic fluid and so on. Therefore, it reflects back. So weird examples I've given. So if you look at something like this, all right, so this one, basically, this is when you send it out. Sent out. So there's 2 reflections, okay? There's 2 spikes. Why is it? One's hit the end, okay? So if I was to draw this bolt, one's hit the end, that's B, and then one has hit a crack in the bolt. So there's a change in density from solid to liquid, and that's caused a reflection. So that's why there's two. And again, same similar question. Okay, why do pulses A and B occur? A is when it hit a crack and came back, and B is when it hit the end of the block and came back. Clearly, the end of the block is going to be bigger. As just use it's this idea of reflections. Why do you get two reflections? There must have been two changes of densities. Okay, another one, and again, you could work at the top from here. We could work at the time. They could tell you the speed. So we know typical speed of sound in air. So this is for sound only and ultrasound. Sorry. Okay, speed of sound in air. Now you don't need to memorize these. They'll normally tell you it's between 300 to 350, depending on weather conditions, so on. Speed of sound in liquids is about 1500, and then speed of sound in solids could be anything in excess of thousands of meters, 4,000 meters per second, depending on the material. Okay, so just be conscious of them. You're not going to have to memorize these, by the way. All right, just need to know about them. So if you look at this now, so we've got this question. A pulse of ultrasound is sent out from an electronic system on board the ship. It takes 0.8 seconds for the ultrasound to be received back. So the time taken to go there must be half of that. So that's 0.4 seconds. If calculate the depth of the water, so they want the distance, which is equal to VT, because all we're using is speed is distance over time, and they gave you the speed. So we just put it all in. So depth, distance is equal to 1600 times 0.4. So nice and easy. Now, if you forget to halve the time, just halve the distance afterwards. But there's got to be a halving, especially if it's an echo or a reflection. So just be mindful of that. If you forget it, obviously you're going to lose 1 mark somewhere. All right. So, but you won't lose all the marks because there's calculations, rearranging, of course, working at maybe there's some unit conversions. All right. So that's chapter 12. Now, moving on to chapter 13. Chapter 13, basics, EM spectrum. Yeah, so make sure you know your EM spectrum. They've gone to town last paper before on gamma rays. Why gamma rays? Because gamma rays is ionizing radiation. Radio waves, microwaves, infrared, visible, and parts of ultraviolet. They're not ionizing, so they're not dangerous as such. Okay, but the one they haven't asked about, which is one they normally ask about. So there's two things that are higher spec. So on this chapter, there's two things: production of radio waves, which came up last paper. Okay, and again, go from our walkthrough. And the other one is to do with X-rays and their properties. Okay, so what do we use X-rays for? Detecting fractures in broken bones. Why do they make good X-ray pictures? Why are they good for taking pictures of you inside? Because they're highly penetrating, so they pass through the flesh easily. But when they get to bone or steel, they get absorbed because the density is greater. So therefore, they create like a shadow picture. Okay, so that's the sort of things they're looking for. So yeah, that's the sort of thing they're looking for. Just how they use, why do we use it? So if you look at this question here, CT scanner uses X-rays. So let's have a look at what the mark scheme says. Advantage of using CT scanners: high quality or detailed, high resolution. Okay, so they're not ionizing enough to cause cancer like gamma rays. Produce slice through the body. Easy to diagnose or see the problem. Now look at the dangers. X-rays are ionizing, so they may mutate cells, cause mutations. So you have to limit how many of these X-rays you have a year. Cause cancer or kill cells. Shielding is needed. So the radiologist, is never in the room when they do this. Okay, so that's chapter 13 in terms of the higher stuff. They've gone through gamma radiation uses of, so I'm expecting X-rays. Or even the others are quite straightforward. Just go through your EM spectrum. Okay, radio waves, production radio waves. I don't expect that to come up again. And just like that, for chapter 12, the other thing on there was seismic waves. Now that was tested last time. Okay, on 2024. So, and they pretty much went through everything about seismic waves, how we use them to understand the structure and the core inside of the Earth. So, I don't expect that again, but just go over the 2024 paper, um, just to go through how it works, why it works, the properties, and so on. So it's not too difficult. Right. So that's chapter 13 done. Okay, so just be mindful of that. Now let's move on to chapter 14. Okay, so here we go. So first of all, the chapter starts off with reflection, law of reflection, and it goes into refraction, wavefronts again for refraction. Hey, can you explain refraction using wavefronts? Again, I've gone through that already on the other walkthrough. And then it was the required practical and reflection refraction. And that's sort of been done to death now for the last 3 years. So what they haven't done for the last 3 years, which is really surprising, is ray diagrams. Okay, so convex lenses and concave. Now, convex lenses are the ones that are really popular to draw. So what does convex or converging? It converges parallel rays to a focal point. Okay, and the distance from the center of the lens to the focal point is called the focal length. This central line here is called the principal axis. Okay, and then you've got a concave lens or diverging lens where parallel rays are diverged, okay, or spread out. Now you're probably thinking, well, how do you work out this angle that it spreads out here or here? Well, what you do when it hits the lens, you chart a line from the center of the lens to the focal point. This bit is dotted because it's imaginary, and then just extend outwards. Okay, so you've got to be able to do that. So let's have a look at the first thing. So we'll start off with convex lenses because those are the popular ones. So if you have something outside 2f, how do you work out where the image is and what properties of the image do you know? So first things first, you draw a line from the top of the image through the center and straight on. So let me just make that straight. So make sure you draw an arrow for each straight line that you draw because it's the direction of the ray of light. Okay, and the next one goes the next one goes parallel, hits the center of the lens, and then from the center of the lens goes through the focal length. So let's see if I got that right. Yeah, that's not bad. So again, draw arrow for each straight line that you've drawn. And here is my image. So what can you tell about the image? First of all, in relation to the principal axis, it's upside down. Okay, so it's inverted, it's clearly smaller, and it's real. How do I know it's real? It's formed on an image or it's on the opposite side of the lens. So I've actually drawn these anyway. So here we go. That's not far off from what I drew myself. So it's inverted means upside down, diminished means smaller, real means it's on the other side of the lens. Okay, what happens now if you bring it closer? So if you bring it 2f, again, I'll just show you. Practice yourselves. You don't need to have graph paper, but usually when they have this on the exam question, they have graph paper. Just get some line paper and draw it yourself. So which way have I gone here? Oh, let's go back. Sorry. Yeah, here we go. So again, from the top of the object, go straight through the middle. Okay, use a ruler, please. And then draw an arrow to show the direction. And another one, go to the center of the lens, a parallel ray, and then parallel ray through that. And then through the focal length, has to go through the focal length on the other side. That's not bad. Okay. Yours is better. It's very hard to control this pen. And here's my image. Notice what's happening to the image. Don't draw a scribbly line here. Make sure you draw nice and neat. So how would you describe this one? This case, that's not bad actually compared to what I did. Sort of trying to do it freehand. Maybe it is bad. So it's inverted, same size, and it's real. And then if you move it inside 2f and f, so hopefully what you noticed is the closer you bring it, the further the image moves away because it's harder to refract and bring the parallel rays to focus. So then when you have it inside f and 2f, again, I'm just going to not even bother drawing straight. So draw your lines, draw your arrows, and then go through. It does eventually, there you go. That's not bad. Yes, that's quite good. So it's inverted, upside down. Now it's magnified. So the length of this is greater than the length of the object's arrow, and it's real because it's on the opposite sides. How do you work at the magnification? You just do so. The magnification is equal to the image over the object height. So just get a ruler, start measuring. Okay, and then what is the one they like to draw? Okay, the hardest one of the converging is what happens if it's inside the focal length. Now you're thinking, well, how do I work out the focal length? They'll tell you it. They'll tell you the focal length is 5 centimeters. Something is placed 2 centimeters from the lens. So it's inside the focal length. Okay, so again, if you try to do it this time, so if you, I'll go through you this time. So straight through the middle first. Okay, draw your arrow, and then draw your parallel ray, and then from the middle of the ray to through the focal length. Notice it's not going to converge. Don't worry, it's not a diverging lens. They're actually converging on the other side. Okay, you'll have a ruler, so you draw it nice and neater. Okay, so how do we describe this one? Nice and straightforward. It's upright. Okay, it's the only one that's upright. So it's virtual, meaning it's on the same side. And it's not actually something you could produce on a screen. Okay, so that could be your definitions. And it's magnified. Okay, so those are your convex. Practice with these. Okay, I'm expecting them to come up. All right. Then you got your concave lenses. So how do you do a concave one? So as I said, first one goes through the center. Okay, and then the next one, parallel ray hits the center of the lens, and then how do you work it out? Go from the focal length to there, and then draw it straight. Use a ruler, of course. Let me just show you, it's easier. So it looks like this. All right, so where the two lines intersect is where the image is. So if you look at the arrow for the image, it's upright, it's virtual because it's on the same side, and you can't see it. So the dotted lines are virtual lines, the bold lines are clearly the ones you can see or observe, and it's diminished, it's tiny. Okay, it's I don't know what another word for that is. Okay, so that is chapter 14. The only other thing they haven't talked about is filters, how do the filters work, and colors. So revisit that as well, please. All right, so I'm expecting ray diagram. So chapter 15, the big one, the one that scares everybody. So let's have a look at this in a bit more detail. Okay, so first of all, we start off with it starts with basics like magnets, bar magnets, permanent magnets, temporary magnets, induced magnetism, magnetic materials, hard magnets, soft magnets, iron, steel, cobalt, nickel, and all that. So that's your basic stuff. I'm not going over that. I'd expect that to be more on a foundation paper, but just you might have to draw a field around a bar magnet, and so on. But really, the thing that they're going to test is the electromagnetism. Okay, so we start off with so these are the slides in my class, so I'm just going to go through these again. So when a current passes through a conductor, it produces its own magnetic field. Okay, so you see this vertical conductor, basically a piece of wire. If you put a current through there, you create circular magnetic field lines. So it doesn't look like a bar magnet. And how do you work out the direction of the field lines? It's called the right angle grip rule. So pretend this straight line is your pen in your hand. The thumb is the direction. You basically grab the pen such that the thumb is the direction of the current, and your fingers, the way direction of the fingers wrapping around, is the direction of the field lines. Okay. So let's just zoom through these. So if you look from a bird's eye view, if the current is coming out the page, i.e. your thumb's pointing to your face or pointing to you, then this is what the field lines will look like. And if your thumb was pointing towards the screen, this is what the field lines will look like, or how your fingers will be wrapping around the pen. Key thing here, reversing the current reverses the direction of the magnetic field. It does not change the size of the field. If you want to change the size of the magnetic field, you change the size of the current. Clearly, bigger the current, the bigger the magnetic field. Okay, so that's nice and straightforward. In terms of where do we use this? So they may expect you to draw the field lines around a straight wire or a conductor. And then, if they're really cruel, it's never come up. It's come up on one of the exam boards. They might ask you to draw the field around not a straight wire, but a wire that's been coiled up. But at any point on the wire, as you can see here, you could actually use right-hand grip rules. So I've only done it 3 places, but you can do it an infinite number of times. And if you add up the cumulative effect of all those, you get a field that looks like this. Okay, so this is a bit tricky to draw. So this is the field around the coil. All right.
Then what do you get if you get lots of coils together? You get what we call a solenoid. Okay, so a solenoid is, think of this multiple times. So think of this field multiple times. Will look like this. Okay, so this thing here. So now, if you look at the field pattern, what does it look like? Looks like a field around a bar magnet. So the field around a solenoid, basically coil of wire, looks exactly like the field around a bar magnet. So what do we know? What do we know about a bar magnet? It has poles. So how do you work out, well, which pole is which? You just put a plotty compass there. If the field lines go out, then you know it's north. Field lines go in, you know it's south. How can you work out the size and shape of the field? Sprinkle iron filings, tap a card that is placed underneath it, and just make out the field lines. How do you make the electromagnet stronger? Because essentially what we're now doing, we're putting a current through a wire to create a magnet. That's called an electromagnet. Okay, how do you make it stronger? More turns, larger currents, and in between here, in between the cores, you'd put a soft iron core. Why a soft iron core? Because it can magnetize, demagnetize easily and quickly, which is what you want, because it's an electromagnet. When you switch the electricity on, you want it to be a magnet. When you switch it off, you don't want it to be a magnet. If you change the positive and negatives here, you don't change the size of the field, you just change the direction. So what was once a north will be a south, and vice versa. Okay, so that's your basics about electromagnet. And the theories here, so how to make the electromagnet stronger, larger current, more turns, use a soft iron core. Reversing the current reverses the poles of the magnetic field only. Okay, so they could ask you, you know, and you probably noticed when you did this experiment, build an electromagnet, when you switch it on and put your hand on the wire, you notice that the wire started vibrating, so there was a force. So what caused this force? What interaction has created this force? Now, the only forces you know in magnetism, attraction and repulsion, and that's because you bring two fields together, don't you? So what's happened then? So you got a current in the wire producing a magnetic field in the wire. So that's what we just talked about. Now, if you place an iron nail in the magnetic field of something else, then the iron nail, because it's a magnetic material, becomes magnetized. So therefore the iron nail becomes magnetized. The iron nail itself will then, because it's a temporary magnet, will have induced magnetic field inside it. So the iron nail produces its own magnetic field. B field, B is for magnetic. So the B field of the wire interacts with the B field of the nail. Therefore, the force is produced. That's what this vibration is when you hold it. And it's a lot hot. It's really hot because there's a huge current passing through. Okay, so use the compass to work out the direction of the field. Use the these paper clips to work out the strength. Because the stronger the electromagnet, the more clips it'll pick up, and that's what you need to do. Okay, give you an example of a question with an electromagnet. So this is an alarm bell that goes dong, 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 dong. It doesn't go dong and stay like that, or go dong. You have to switch it off and then switch it back on. Because there's no one sitting by the switch constantly pressing it to go dong, 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 dong. It does it automatically. So you have to think about, well, how do you do it? So first of all, you close the switch here. So now you've got a current flowing through it. That means the electromagnet is switched on. If the electromagnet is switched on, the iron arm, which is magnetic, gets attracted to the electromagnet. And in doing that, the hammer hits the gong. But in doing that, as the iron arm moves away from the brass contact, it loses contact. Therefore, you have an incomplete circuit, so the current stops flowing. So therefore, once the hammer has hit the gong, the iron arm is not attracted to the electromagnet no more because it's switched off. So therefore, it goes back to its original position, goes back to the brass contact, makes contact, and the circuit comes on again, and it repeats and repeats and repeats. So there's your description here. Okay, put it in as many or as less words as you want, but essentially, switch it on, becomes an electromagnet, attracts something. Cause and effect. Okay. Another example, when you see those bolts still, you know, when you buzz someone in through the door. Okay, how does that work? So basically, you switch it on here. So switch inside the flat. Someone's called in. I'm coming in. You switch it on. The electromagnet magnetizes, attracts this iron bar. So this iron bar goes to the left, and because of these pivots, this stretches. And the steel bolt, because of this pivot, the steel bolt moves to the right. So therefore, you let the person in because you've unlocked the door. Okay. They'll buzz for about 5-6 seconds, assuming you come in, and you'll close the door and you're trying to lock it. Like, don't worry, you put your finger off the switch inside here, this stops becoming an electromagnet. This stops getting attracted to it. The spring recoils, comes back, forces the iron bar back, and then it causes the steel bolt to go to the left. Okay, so, and again, the what ifs. What can you do to make it stronger, or can you do to make it weaker, etc. All right. So that was electromagnetism, and that was the reason they're using it. Now what's left is what we call the motor effect. Okay, so the motor effect, we sort of talked about it because that's what you experienced in the electromagnet when the wire was vibrating. So you've got to give it an explanation first. So motor means motion. So you're creating motion because there's a current in the wire. So current in the wire produces a magnetic field in the wire. The magnetic field of the wire interacts with the magnetic field of the magnet. Force is produced, direction given by Fleming's left-hand rule. Okay, so Fleming's left-hand rule, make sure you can use it. So here, in this case, if you look at the picture, the current is going that way. So in a 2D sort of visual, that means the current is going into the page. So we represent that by looking at the cross. Okay, if the current was coming out the page, you'll see a dot. So therefore, use your Fleming's left-hand rule. First finger, field of the magnet. Second finger, the current of the conventional current, positive to negative. And the thumb is your motion, which way the wire is going to move. Okay, so north to south, point your first finger north to south. Second finger, point to the screen. You notice your thumb goes down. So how do you make the force stronger? Larger current, more wire or turns, so turn into a coil, and a stronger magnet. You get the maximum effect if you think about your Fleming's left-hand rule. I'll just show you now. Maximum effect when these fingers and the finger and the thumb are right angles. Okay, if they are not at right angles and you try to do like mimic a little gun, like when you play cowboys and Indians or whatever, if they're parallel, then you get no force. And if you reverse one of these factors that we mentioned here in Fleming's left-hand rule, you'll reverse the force. So if you reverse the current in this picture, the force will now be upwards. If you reverse the magnetic field only, you flip the poles, so the current was as in the picture, then the force will be upwards. But if you reverse both the magnets, so the north was now south and the south was now north, and the current was going out to the page, they'll cancel and they'll be down again. Okay, so you've got this picture here. That will produce the same force as this one here. So two reversals cancel each other. So here, in the class, we just went through quite a few examples. Cover up the green answers, see if you can have a go yourself. Now, if you're worried about using Fleming's left-hand rule, you'll only have to be 1 mark. Okay, the first few marks will be, can you give me an explanation? That's like a 3 marker or 4 marker. The what ifs, another 2 marks, maybe 3 marks. Okay, this will be 1 mark at most. All right, so I mean, like I said, there's no harm in trying, so keep trying. If you're not trying to do it, then maybe I'll come on video and I'll try and do it on the screen with you. So just be mindful, like this one here, this is not a trick question, and this one here, I put electrons instead of on. Electron means electron flow, which is negative to positive. That means your second finger points in the other direction. Okay, so if the electrons are flowing to the left, the current is flowing to the right. Okay, so just be mindful of that. All right, and same here, I put electron, not what do you call it, current. So make sure you have a go at those. What do we know? So we said the stronger the magnetic field, the stronger the force. Stronger the current, the stronger the force. The larger the length or more length of wire or more turns or more coils, the stronger the force. So you got this formula equals BIL. Okay, so make sure you can use it. It's given to you now. And here's a sort of classic question. Okay, so look here, unit conversion 60 micro says this, that's times 10 to the minus 6. Forces in the correct units, giving you the current, which is correct. And they're going to ask you to rearrange. So don't expect a simple work out the force. Maybe if they do, you're lucky, but expect a rearranging. And then let's move on to the next one. So this is an example of the motor effect. Okay, so here is what we call electric motor. All right, so what's going to happen? You see the 2 red lines, that shows you the direction of the current. You've got the field north to south. Okay, so clearly in one of the red lines, the force is going to be in the opposite direction to the other red line because the current has been reversed, isn't it? So one will go up, one will go down. I'm sure you can work it out. If not, They'll probably help you. They might even draw the rotation that it's rotating. If not, you can have a go. Okay. Whichever one you say is up, draw the other one down. Okay. Even if you're wrong, you're still going to get a mark for proving that it will rotate. So what's the description of this? The first bit, current in the wire produces a B field in the wire, B field in the wire interacts with the B field of the magnet, force is produced, and then you've got to give context to get the extra mark. A force on either side of the coil creates a moment because one force is up, one force then creates a rotation, causing it to rotate. Okay, so here it is in a bit more detail. Okay, so you've got a DC electric motor here and here. I've sort of tried to illustrate positive, negative. So the current is going into the page. So can you see current goes into the page on this side, south to north, north to south, sorry, and force is up. If the force is up on this side, that must mean the force is down on this side. Okay. What can they ask you here? They can ask you which way it rotates, and they can ask you what these two things are. So this ring, which has been split, hence called split ring commutator, give the definition, please. That's what they're going to ask about it. And the brushes, what do? Well, as the coil is rotating, you don't want the wires to rotate because they'll get trapped. So you want a way to be able to rotate this the coil while the wires stay in place. They just maintain electrical contact while the coil is spinning. So those are the only definitions they can give you. Now, this has not come up. Last year, instead of this, they did the loudspeaker, okay, which is a bit surprising because the loudspeaker was quite tough, and that was actually the generator effect, not the motor effect. So maybe be prepared for a motor effect question. Okay, and then what we have. Yeah, so someone asked me, well, how does a split ring commutator work? They're not going to ask you in depth. All you just need to know, the split ring commutator reverses the current every half cycle to keep it spinning. The rest of it is your typical motor effect description. And as this coil is rotating, if you have it connected to an axle and a wheel, and you have 4 of these on 4 wheels, that's how an electric car works. Okay. Right, loudspeaker. Again, this is how it works. So this is a bit unusual. Now, this came up 2023, the loudspeaker. Okay, the diagram bit, now, not the description. So make sure you can write the description. Now, look at the first 3 bullet points. It looks exactly like this one here. Okay, so this is your go-to knowledge. So make sure you get that down. And then you've got to give context. The last point is context. So here you have an AC supply, not a direct current. So the AC constantly changes the direction of the current, causing the force to constantly change direction, which means the cone moves back and forth. Vibration creates the sound. Okay, so can you see? If you're not sure how it works, at least explain why it moves. Okay, so regurgitate, write it 50 million times, whatever. So that's the motor effect. Loudspeaker maybe come up, but certainly I'm thinking if they're going to ask anything, it's going to be the DC electric motor, an explanation about the split ring commutator. Okay, maybe. But last year it was the generator effect question, especially. Okay, so now let's move on then. So what I've done here, and I did it for my class, on the left-hand side is a summary of the motor effects. So basically what we've just talked about, using a current in a wire, in this wire here, to produce a magnetic field, which then produces a force because it interacts with the field of the U-shaped magnet. Here, what are we doing now? So the generator effect, if you think of Fleming's left-hand rule, the motor effect is using the first finger and the second finger to produce the thumb. The generator effect is using the thumb and the first finger to produce the current. So where we talked about, if you look here, to make a force larger current, stronger magnet. Here, to make a current larger, so to make a bigger middle finger, you need a bigger first finger and a bigger thumb. So larger force, that's the thumb, stronger magnet, which is the first finger, and more turns for both, because that means more interaction. Same sort of conditions in terms of reversals. So we talked about, for the motor effect, there is this formula, I think it was BIL, but there isn't a formula for the generator effect. Okay, so that is an A-level formula. It's called Faraday's law. So you don't have to worry about that. 2 examples of the generator effect. One is the microphone, which came up 2024, so I'm not expecting that. And the dynamo, surprisingly, came up 2023. Okay, and that is a bit of a nasty question. All right, so I'm glad that I'm presuming that won't come up. So I'm expecting either the AC generator, which I'll go over in a minute, or the DC electric motor. Okay, simply because they haven't tested those two. All right, so let's have a look. Now, how do you induce a voltage or produce a current? So two ways. If you think of Fleming's left-hand rule, to produce the current, which is the second finger, you need the first finger, which is a magnet. In this case, we've got two different types of magnet, and you need the thumb, which is movement. So either the wire moves relative to the magnet, or the magnet moves relative to a stationary wire. So move a wire up and down, perpendicular to a B field. It has to be perpendicular because it's parallel, you get no cutting. Or move magnets in and out of the coil. So that, therefore, the wire of the coil in both scenarios cuts. So if you look at the description, the wire cuts the B field lines, induces a voltage, and if it's connected to a circuit, in this case, the arc is connected to a voltmeter, so it's a complete circuit, produces a current. That is your go-to explanation for generating a current, producing a current, inducing a current. Be careful with the words they use. So let's have a look how does the AC generator work. Now I'll put the DC generator on the left here, just for you to look at. Okay, so we talk about the split ring commutator. The AC generator has a slip ring. You don't want a break in the string, because if you do, that means you now lost the current you've generated in the coil by cutting the field lines of the magnet. So what's the description? First three bullet points, as we said, coil cuts the magnetic field lines, induces a voltage. If the circuit is complete, current produced. So that's your three basic go-to descriptions. The last point is your context. So as the coil spins, changing direction causes induced current to change direction. Okay. So therefore, what do you call a current that constantly changes direction? You call it an AC current. So if you look here, an AC generator produces a alternating voltage and therefore will produce an alternating current if the circuit is complete. How is a dynamo different to an alternator? And this came up. We even asked you to plot the graph. That was 2023. Will they ask you again? Seriously doubt it. It's quite a tough question. That's probably why the grade boundaries, actually the grade boundaries are quite generous actually. So here, rather than going in the negative, the split ring commutator ensures the induced voltage is always positive. So you get positive induced voltage and a positive induced current. So dynamo, I'm not expecting. AC generator, quite possibly, because they haven't tested that for a couple of years. And I said DC electric motor for the motor effect haven't been tested for a couple of years. So now let's look at, well, for the motor effect, we had the loudspeaker. Okay, what's the opposite of a loudspeaker? It's a microphone. So a loudspeaker uses current to produce sound waves. A microphone uses sound waves to produce current. So sound waves hit the cone, the coil moves to the right, so it moves that way, cuts the B field lines, so the coils here will cut the magnetic field lines and induce a voltage. If the circuit is complete, you get current. But what does the sound waves do? The compressions and rarefactions causes the cone or the diaphragm to move back and forth, vibration. So you've got a change in direction, therefore you've got a change in the direction of the induced current, and therefore that's what we call an AC current. Okay, so a loudspeaker uses AC current to produce sound. A microphone uses sound to produce AC current. Okay, so right, so moving on, I think that's the same one. Okay. So then that is your EM induction or generator effect done. Then the last bit is, well, when you produce this electricity using an AC generator, what do you do? So you've come across this already. This was on paper one also. Wouldn't come up again. This time it'll come up because we're going to talk about the transformers in a lot more detail. So here, power station produces 25,000 volts. These are just typical values, they're not exact. 25,000 volts considered low voltage. Low voltage means high current. High current, what does current do to a wire? Heat it up. That's not good because it means heat energy loss, thermal energy loss, which is inefficient. So what do? You step it up to 400,000. High voltage means low current. Low current means less heating effects, less energy loss, and it's more efficient. And then 400,000 volts you don't want in your house, you catch fire, so you have to step it down to 230 volts AC 50 hertz, which is mains electricity. So that was the big picture. So essentially what happens in the power station is the AC generator. Okay, so now let's move on. Well, what about the transformer? So they can ask you a number of things. First of all, they can ask you the structure, what it's made of, primary core, secondary core, both made of copper because they're good electrical conductors because you're passing a current through them. The soft iron core, why? Because these are magnetized, demagnetized. And then the primary is connected to an AC supply. The secondary is connected to whatever you're trying to produce the electricity for. I just stuck a ball bead. It might not be a ball bead. It might be the national grid. So make sure you can tell the difference between a step up and a step down. Step up, more turns on the secondary, so more voltage on the secondary, so less current on the secondary. Step down, more turns on the primary, more voltage on the primary, less current on the primary. Okay, so put these in words, put these like this in simple form, it's up to you, it's not a problem. Okay, so then first they'll ask the structure, then they'll ask how it works. So this is your description. Again, regurgitate it. So if they ever ask, well, how does an alternating current or a current on the primary produce an output on the secondary? So AC in the primary core produces changing B field in the primary, because don't forget, the current in the wire produces the magnetic field in the wire. Because it's an alternating current, it produces an alternating magnetic field, which goes big, small, and the field direction is changing because the current is going positive to negative. That changing magnetic field gets transmitted through the soft iron core, because that's good at transmitting, magnetizing, demagnetizing, passing the magnetic field along. So the changing magnetic field now comes to here, gets cut by the secondary field, secondary coil, induces a voltage. If the circuit is complete, to produce a current. Now, notice the current on the secondary is larger. Why is it larger? Because there's more turns, more voltage. If the voltage is larger, the current is smaller, but the power on the secondary is the same as the power on the primary. The power is not increased or decreased, it's just changed form. So if you increase it, because power equals current times voltage, or power equals IV, if you make the voltage bigger, you have to make the current smaller because the power stays the same, because it's conservation of energy. It's not creating anymore, it's just changing the form of it. Okay? Now, why do we use DC? When the switch on the primary coil is closed, then a B field is produced. If you use DC, this is what would happen. This change in B field is cut by the secondary coil and induces a voltage. So basically, when you go from zero current to a value, let's say 10 volts, steady 10 volts, then what you find is the field goes from nothing to big. So there's a change in the magnetic field. And therefore, that change in the magnetic field gets cut by the secondary. But after that initial point, the field remains constant because the voltage is at 10 volts. So therefore, there's no change in magnetic field, so there's no field lines cutting, there's no induced voltage, so it goes to zero. So basically, AC generators only work, transformers only work on using AC. And then the last thing, what could they do? They could ask it to use the formula. All right, so again, cover the answers up in red, have a go. Use the formulas if you want, or just use this ratio method that I've used. And I went through this on the walkthrough paper. Okay, so whatever you do to the turns, you do to the voltage, or whatever you do to the voltage, you do to the turns. Okay, but the current is opposite. So the current, if these are times by 6 for the voltage and the turns, the current is divided by 6. If you go from primary to secondary, so use your common sense. Okay, and again, I've done another question. Cover the red answer up and have a go yourself. See if you can work it out. This is a bit trickier because this voltage is turn and currents. Okay, and this was a question many moons ago. Okay, it wasn't a recent one. So expect a transformer question. They're quite nice. Operation of transformers. So transformers, they didn't go into much depth, so maybe we're expecting that. Okay, so that's chapter 15. And then we're left with chapter 16. What is there for chapter 16? Now, we talked about this. So what they haven't asked yet, how do you go from a to a protostar to a main sequence? That hasn't come up a lot. What's come up recently? So I'll put a question mark here. What has come up has been life cycles. The life cycle of stars came up 2 years in a row, and for big stars and stars sizes of our sun, and redshift has come up. So these have come up a lot the last 2 years. Redshift expanding years, but they're really easy, really straightforward. So go over it. Okay, it shouldn't be a problem. This one, what you need to know, this is clearly a cloud of dust and gas. Cloud of dust and gas. Bring lots of clear dust and gas together, temperature goes up, pressure goes up, and it forms a protostar. Protostar, not quite hot enough. For fusion. No, fusion hasn't come up in has not come up in detail, so I'm expecting that. Make sure you can explain that. Two hydrogen isotopes fuse to become a helium isotope. There's a missing mass or decrease in the mass which gets converted to energy. Conditions needed. So here, what do you know about the main sequence star? Now, what pulls all this dust and gas together is gravitational forces. So I might ask you who caused it or how is it caused? How is it clumped together? Gravitational forces, because they're huge amounts of mass, so they get attracted towards each other. Main sequence star is where fusion occurs. So here, the gravitational force, gravity inwards, as you put forces, is equal to fusion pressure outwards. And that's what we call a main sequence star. So they haven't asked that yet. So maybe they could ask that. Maybe they can ask detail about what is fusion. Okay. The other thing they haven't asked, a bit surprising, is orbits. Okay, orbits. What do we need to know? Let's say you got the sun. Okay, got the Earth. Why did the Earth move in circular motion? There's a force of gravity inwards. Okay, so the force of gravity in right angles. So the force is perpendicular to the velocity or the speed. Therefore, it causes it to move in a circle. Now, the speed is constant, but direction is changing. So if the direction is changing and the speed is constant, then you have a change in velocity, so velocity vector. And if you have a change in velocity over time, that's called an acceleration. Okay, what do we call this force towards the center? That's known as the centripetal force. Okay, so any force that keeps something in a circle is called centripetal force. In this case, the centripetal force is gravity. So they haven't asked about orbits yet, so I'm expecting that. So that's my load in on paper 2 predictions based on patterns and sort of what's been going on for the last few years and so on. Okay, so for the rest of you, good luck with your paper 2. Any questions you want to ask, just drop me an email at the end of the email and I'll make another video for you. Otherwise, good luck or good luck wherever you in the future also. Thank you.